So what was the symbol for molality? Yeah, little m. So little m is molality. If you read the textbook or go online, sometimes a lowercase b is used. We'll stick with a lowercase m though. So molality was number of moles of solute. What's the symbol for number of moles? N divided by kilograms of solvent. Okay? So moles of solute divided by kilograms of solvent. So the two properties we want to discuss are freezing point depression and boiling point elevation. So when we dissolve something, we'll say in water, for our example so far, the solute causes the freezing point to be depressed. So does it make it go up or down? Down. So it decreases the freezing point. It causes the boiling point to be elevated. So does it make the boiling point go up or down? Up. So remember those two phrases, freezing point depression, boiling point elevation. Freezing point down, boiling point up. So let's talk about kind of what that means to be, say, the freezing point is depressed. So first of all, what is the difference on a molecular level in liquid water and solid water, ice? Yeah, the speed of the water and also the arrangement of molecules, right? So if we think about liquid water, if I just draw little dots for water molecules, the water molecules, are they arranged any certain way in a nice pattern? No. Are they sitting still? No. What are they doing? They're just moving around, right? A nice little arrow, right? But then, as I begin to remove energy, the molecules start to do what? Slow down, okay? So we'll say decrease. So how do I decrease the energy? I decrease the... Okay. Temperature is what we typically describe, okay? So we decrease the temperature. So if I decrease the temperature enough, it's going to freeze. When they freeze, the molecules freeze, do they continue to move around and slide past each other? No. Do they stop moving completely though? They still vibrate, okay? But they're going to be stacked in a nice little pattern, okay? So we get an ice crystal. So a nice ice crystal, you can see through it, it's nice and clear. Okay, so a nice regular repeating pattern. So that is the process of freezing. At what temperature does this happen for water? 0 degrees Celsius. So when we add a solute, if the freezing point is depressed, it's going to be greater than or less than 0? Less than 0. Okay? So let's think about if I take some water and I put sodium chloride in the water. What does sodium chloride do when you dissolve it in water? The D word. Dissociates. So in the water, I'll just draw one sodium chloride. I have Na plus and Cl minus. Okay, the sodium chloride dissociates. So then, what part of the water molecule is attracted to the sodium? The oxygen or the hydrogen? The oxygen. So the oxygen is close to the sodium. The hydrogen is close to the chlorine. I drew those a bit too close together, but there should be a little space there. Are they chemically bonded together though? No, they're just attracted. Okay. So if they're attracting, the sodium and the chlorine do two things. First, by attracting the waters, they prevent the waters from forming the nice repeating pattern necessary to freeze and form ice. And also, they physically block the formation of the crystal. So imagine if you have things that aren't water molecules in here. So they could block the formation of that ice crystal. Okay, does that make sense? So by those two processes, they are preventing the ice from forming. Now, can it stop the ice from forming forever? Now, if we decrease the temperature enough, eventually it's going to freeze. Okay? So where in your lives, or your parents' lives, have you encountered this quite a bit? On the roads. What do we do, not so much here, more in the northern states, when it gets cold? You put salt. The salt dissolves in the water, okay, And the water no longer freezes at 0 Celsius. It freezes at a much lower temperature. So it prevents the roads from icing over. Okay? So we know that happens. We've seen it. But we need to think about by how much. So we said it cannot depress the temperature or freezing point forever, but it can for a certain amount. So we need to calculate by how much we can lower the freezing point. So we have a formula for that. So our formula is delta T. So what does delta T stand for? So what does delta T subscript F stand for? Yeah, so change in the temperature of freezing. So probably a better way to say it's change in freezing point. That's the way we would say it. It's change in freezing point. Okay. So the change in freezing point equals KF. So KF means a few different things in chemistry, actually. Here, it's referring to, you don't have to turn back, I'll just show you. 2 pages back in the notes, when we started, there was this chart at the top. So this refers to the molar freezing point constant, KF. And you have these values here, okay? So, of these values, we most commonly use this one, 1.86, because it is specific to these solvents. We typically use water. So what this constant tells us, because the units are degrees Celsius per mole, M-O-L-A-L, is saying for ever how much the concentration changes. So for 1 molar concentration, this is how many degrees Celsius temperature changes. Okay, but it is specific to each solvent. Okay, so most often we'll plug in 1.86. But if a problem says acetic acid, you'll use 3.90. Okay. So then it's KF times lowercase m. What does lowercase m stand for? Molality. Then a new one times lowercase I. Lowercase I, it's not an imaginary number. It's called the Van't Hoff factor. So not the square root of -1. We don't get those in chemistry very often. So, no, in math it is, in chemistry it's not. So, in simple terms, the Van't Hoff factor is the number of particles a compound produces when it's dissolved in water. So let's do some examples and it should make sense. So write out NaCl, MgCl2, AlCl3, C2H6, and then KNO3. And then we'll write down the I value for each of these compounds. So when sodium chloride dissolves in water, does it dissociate? Yes. How many ions does 1 sodium chloride make? 2. So my I value is 2. Does magnesium chloride dissociate in water? Yes. So how many particles does it produce? 3. 1 magnesium, 2 chlorines. Do we all see where this is going? Yeah. So, or the number of particles, not necessarily ions. So AlCl3, the I value is 4. Now, C2H6 is covalent, and it's not an acid. So will it break apart in water? No. So 1 C2H6 particle makes how many particles in water? 1. Okay. So anything that is a non-electrolyte, or non-electrolyte means it does not dissociate or ionize in water, my I value is going to equal 1. Okay. Anything that does not break apart, I is just 1. Correct. Acids ionize though. So the acids break apart.
So they do.
Yes.
What else doesn't? Anything else?
So KNO3 is an ionic. Yeah. So will it dissociate? Yes. But what kind of bond holds together the nitrogens and oxygens in nitrate? Covalent. Right. So a nitrogen oxygen bond is covalent. So will the nitrate itself break apart in the water? No. So how many particles do I get from KNO3? Just 2. Not 5. Do we all see why it's just 2 and not 5? The polyatomic ions do not break apart. Okay? So now let's think about what I'm solving for. I'm solving for delta TF. That is the change in freezing point. So let's say I do a calculation and delta TF equals 3.2 degrees Celsius. If delta TF equals 3.2 and I'm using water, is 3.2 my new freezing point? If I said that, that means the freezing point went up. Okay. It's the change. So what's the initial freezing point? 0. So what's the new freezing point? Negative 3.2. So for water, we can just take the change and make it negative. Because if it goes down by 10, the temperature is negative 10. If it goes down by 20, it's negative 20. Okay? But that trick only applies to water because water has a freezing point of 0. Really, we should be saying we'll take the freezing point and subtract 3.2. Okay? But most of our problems involve water, so we can just change the sign. Okay? Does that make sense? Yeah.
So are you going to do with the freezing point going up or anything like
No.
that? So
It's just going to go down. Yeah.
subtracting?
The only difference would be if it were like acetic acid, you would take 16.6 then subtract the 3.2 there. Okay. Questions? So turn over, let's look at a few examples of this before we go on. So look at that assignment. Where's the other place you might have seen this in your day-to-day life? In the summer, maybe for 4th of July.
Fireworks.
Fireworks.
Watermelon.
Does anybody make homemade ice cream?
Oh, yeah.
You gotta use the ice cream freezer where you put the salt and the ice. So you've probably seen this before. Anyway, so look at number 1. A solution consists of 10.3 grams of non-electrolyte glucose dissolved in 250 grams of water. What is the freezing point depression? So am I asking you for the new freezing point? No. I'm asking you how much it went down. Okay. So our formula is delta TF equals KF times M times I. So let's get the two easy numbers first. Where do I get KF from? Just the table. That's easy, right? So it's 1.86 degrees Celsius per molal. And what is my I value? Just 1. Does C6H12O6 dissociate in water? No. So 1 glucose makes 1 glucose. It doesn't break apart. Okay. But now I need the molality. So I need the number of moles divided by kilograms of solvent. Do I give you either of those numbers? No. Do I give you grams of solute though? Can you convert from grams to moles pretty easily at this point? Hopefully. So go ahead and do that. I'll help you out. 180.18 grams. Merry Christmas. I hope that's right. First period told me that, and I just trusted it the rest of the day.
Would we get a different answer later on?
Yeah, that's true. So then, when you solve that, how many moles do you get? 0.0572. Okay. So molality is number of moles divided by kilograms of solvent. How many kilograms of water do I have? 0.25. So I get 0.229 molal. Now can I just plug in? Yeah. So go ahead and type it in, make sure you get it. 1.86 times 0.229 times 1. Malal cancels Malal. So what units am I left with?
Celsius.
Is that a logical unit for change in temperature?
Yes.
Yeah. So you should get delta T is 0.43 degrees Celsius. So that's my delta T. What is my new freezing point if I ask you that? It would be negative 0.43. Okay. So did it change the freezing point very much? No. If glucose had somehow broken apart, would it change it much more? Yeah, that value would be larger. Okay. Questions on that? Let's look at 2. In a laboratory experiment, the freezing point of an aqueous solution of glucose is found to be negative 0.325 degrees Celsius. What is the Malal concentration of this solution? So we're just solving for little m now. So what is my delta TF value? It's just 0.325, not negative. So it's 0.325 degrees Celsius. If you plug in the negative, your concentration would come out with what sign? Negative. Can you have a negative number of moles per kilogram of solvent? No. You probably would recognize this wrong and just take the negative sign off. That would work here, but it won't always work. Why would it not always work? Or when would it not work? If we didn't have water. Okay. For water, the delta T and T are the same with different signs because the freezing point is 0. But for other compounds, that wouldn't work. Okay. So delta T equals Kf, so 1.86 degrees Celsius over m times molality times 1. So pretty straightforward calculation. Just plug it in, and you should get 0.175 malal. So another way to word it is, what concentration of glucose do I need to drop the temperature by 0.325 degrees? That's a way of wording that differently. It means the same thing though. Would I need the same concentration of sodium chloride to drop at that temperature? No, because I would be 2 for sodium chloride. Okay. Questions on that one? Let's try one more together, then we'll take some more notes. So look at 3. What's different about 3 and everything else we've done? There's something. It's not water. It's an ether. Okay. So because it's an ether, that changes 2 things. First, and most importantly, it changes the constant. Okay. So can I plug in 1.86 for number 3? No. Where do I find the constant? It's in the table. Also, can I just take the delta T and make it negative? No, because the freezing point for ether is not 0. Okay, so let's do this one together. So delta TF equals, somebody help me out, 1.79 times, do I have the molality? No. Do I even tell you what it is? Does it matter? Because I tell you the number of moles. And I tell you it's a non-electrolyte, so it's not going to dissociate. Okay? So 0.5 moles makes 0.5 moles of particles. So I need to do moles divided by kilograms of solvent. How many kilograms of solvent do I have? 0.5. So 0.5 over 0.5 equals 1. So 1 malal. What is my I value? 1. So my delta T just equals 1.79 degrees Celsius. But my freezing point is not negative 1.79. How do I find the freezing point? Subtract it. So go to the table. What is the freezing point for ether? Somebody help me out. Negative 1. Say it. 116.3 degrees Celsius minus 1.79 degrees Celsius equals negative 118.1 degrees Celsius. Hopefully. Okay.
Well, you get negative 100.
I'm sorry?
You get negative 116.3.
From the table. So that table that's the KF values has a column for freezing points. It's just the freezing point for ether.
So because of, how do you know, I didn't see where it
Yeah,
said.
I didn't see it.
It's because ether looks like the word ether. So you probably didn't recognize that as a chemical.
You kept saying
I
that.
kept saying that, and I was like, what is he saying?
Yeah, I was like, what?
Ether. Okay.
What is ether?
500 grams of ether.
Yeah, I thought it was like either is
Looks like a little-
either are the solvent.
Looks like a little bat.
Wait, but what is it? Like,
It's like a little bat, just a liquid.
a liquid of what?
Ether.
Like it's an element?
It's a molecule.
I never heard
Kind of
of
like
it.
buy at the store?
Yeah. It's a solvent. If you paint a lot, you probably have it.
Is
Anyway,
it dissolved?
it dissolves some things. Yeah. So go back to boiling point elevation now. The good news is it's very, very, very similar to freezing point depression, just the opposite direction. So freezing point, we looked at the liquid to solid phase change. Boiling point, we'll look at the liquid to gas phase change. So if I have water and I want to boil it, am I going to increase or decrease the temperature? Increase it, which is going to do what to the motion of the particles, or the molecules? It'll speed them up. Eventually, they'll gain enough energy to leave. And when they leave the water, they become gas, so water vapor. Okay? So think about now, if I have a sodium and a chlorine down in here. Is the oxygen attracted to that sodium? Yes. So is it going to make it more difficult to leave the water if it's being attracted to the sodium? Yes. That's one reason. And also, if the sodium is physically blocking the water from the surface, can it escape if it's not on the surface? No. So that's the two reasons why it kind of does that. So now, instead of requiring a lower temperature to freeze, we have to add more energy to evaporate or to boil it. Okay, does that make sense? So now the formula is pretty much the exact same. So delta T, not delta T F, delta T B equals K subscript B. There are two KBs, one here and one that we'll use in May for acids and bases. Where do I find that KB? The table. Times M times I. Okay? Easy, right? Let's do one together. So let's say 3.0 grams of NaCl are added to 1 liter of water. So this is a realistic situation. Do you cook, or your parents cook, they might salt the water when they boil pasta. So I want to know, what is the boiling point? So what's the first step going to be? Yeah, grams to moles. So 3.0 grams NaCl. 1 mole NaCl is 58.44, is that right? So around there. You just gonna trust me? I'm glad somebody does. So how many moles do I have? 0.0513. 3 moles. Then I need kilograms of solvent. 1 liter of water weighs how many kilograms? 1. So divided by 1 kg equals 0.0513 lowercase m. So then I can say delta TB. So what's my KB value for water? What's the molar boiling point elevation constant?
100. Well, I mean,
Not the boiling point, the constant.
oh, okay.
0.512? Okay, 0.51 degrees Celsius from Malau, just from the table, times 0.0513 Malau. What's my I value? It's not 1, it's 2. Sodium chloride makes 1 sodium and 1 chloride makes 2. So before you even type it in, you can probably see this is not going to be a very big number, right? Huh? Somebody help me out. 0.052. Okay, that is my delta TB. But I ask you for the boiling point. So what is the new boiling point of this solution? Yeah, 100.052 degrees Celsius. And so 100 is the boiling point of water. If you don't know it, it's listed in the table. You probably should know it. Just add 100 plus this. That gives me the new boiling point of that solution. Okay. So did the boiling point change? Did it significantly change it though, in a noticeable way? No. Okay. So it's not a significant change. Because we added a very small amount of salt to a fairly large amount of water. Okay. So when they salt the roads, you make ice cream, you add a lot of salt relative to the amount of liquid. Okay. Questions about that? So you still got 20 minutes. So go back and look at those assignment problems now. These should be pretty easy calculations for the test.